All right, so today we're going to be starting on loops, which is module 3, that's what this takes us up pretty much up to the first exam in the 5th week. We'll have more information on how that 5th week, that exam week, is going to go, but you will have an opportunity to turn in one lab and one hack for reconsideration if you screwed one of them up. So look forward to that. Don't screw any more of them up if you've already done one. But that's the limit, right? We want you to do that on week 5 as preparation for the first exam on that Friday. Yeah, go ahead.
Let's say you have all of your hacks are really good, but you have 2 labs that you missed. Would it be possible to change that hack you're offered into another lab?
Probably not. I mean, there's a limit there for a reason. But if you have another reason for why you might not have done lab 1, for example, then come and talk to us. But also note that this redo opportunity, traditionally in this class, what we've done with this redo opportunity is we haven't really announced it until the end of the course. And then at the end of the course, we say, all right, you can go back and you can turn in one hack, one lab or something like that. And it turned out that nobody ever did it, right? Because they had failed the course at that point without that redo. And so what we did this semester is we moved it up to the first 4 weeks so that you know that if you falter, you're not done with this course, right? You can go back and you can fix one thing, all right? After your first exam, though, that's it. The training wheels are off, right? You need to make sure that you're doing everything every week from then on. You're not going to have another redo opportunity after that first exam. It also serves as a way that you can practice and make sure that you absolutely understand everything in the first 4 modules for the first exam, right? For everything from the getting started, basic input, output, conditionals, and loops, right? Again, the way that it works is we'll publish more information when we get there, but basically there's no lab and hack due that week. Instead, you go there and you show one of the LAs that you fixed your stuff and they update your grade, right? And that's how we're going to work it. So look forward to that opportunity if you have not done as well as you wanted to on a lab, not done as well as you wanted to on a hack, but also at the same time, don't be thinking that you got that in your back pocket, right? Don't screw off with, don't blow off like hack 3 or whatever this week, or hack 4 the next week, thinking, I can redo it, right? Don't do that to yourself, right? Make sure that you're staying on top of the material throughout the entire course. And remember that that opportunity is not after the first exam, okay? To continue on our last module before that first exam, we'll also tell you how that exam is going to work closer to the date. Loops. The first exam will cover everything up to and including loops. A loop is a way that you can take a piece of code and you can repeat it, right? If you need to do the same thing 4 times, maybe with different variables or different values, you don't cut and paste the same piece of code 4 times. Instead, you write a loop that repeats the one piece of code over and over and over again until some condition is satisfied or is no longer satisfied. With loops in any programming language, there are 4 basic elements, right? I'm going to go ahead and use the analogy of running around in like an oval racetrack, right? You're running around the track. The initialization statement is where it begins, right? You start running somewhere, right? That's if you've got a loop, you got to start somewhere. A continuation condition is, do I keep running, right? The coach says, oh, you need to go 10 laps. You've only done 1 lap. All right, keep going. You've only done 2 laps. Keep going, right? You've only done 3 laps. Keep going. You keep going until you've hit the number of laps that you need to actually run, right? That's the continuation condition. Continue this loop. Then at the end of it, when you've run your 10 laps and it's done, the coach says you're done, right? Then that's the termination condition. That's just the opposite, right? Continue until you are done. That's the termination condition. Just like a negation operator in conditionals, equals versus not equals. They're just complements of each other. An increment or an update statement means that you're making progress towards that termination condition, right? I'm running lap 1, lap 2, lap 3. I am keeping track of the number of laps that I'm running so that I'm making progress towards that 10th lap. If I don't, if the coach just keeps saying, no, run one more, run one more, run one more, right? Am I ever going to stop? No, not if I'm not making progress towards that termination condition. And then finally, the fourth part is the thing that you're actually doing, the loop body. That code executes for every iteration of the loop. There's a nice word, not keyword for you, but that's what we call one iteration of a loop. One running of a loop is called an iteration. Just to get into it, let's go ahead and look at a basic for loop. For int I equals 0, I is less than, say, 10, less than or equal to 10, I plus plus. Oops. We'll understand the syntax here in a moment. I just want to get this loop going and so that we have something to work with here. Printf, lap, number, and then I'll print out the lap here. And I'll print out I, okay? Now this is called a for loop. Guess why it's called a for loop? We use the keyword for here, right? Now this is saying for those three elements, do the following. For I starting at 1, and while I is less than or equal to 10, continue adding 1 to I. We'll understand the syntax as we go into it in detail here. So this is going to print out, looks like I've lost my terminal here. That's all right. I'm going to go ahead and open up a new one. There we go. E. All right, I'm going to compile this demo. There we go. And run it. So what's it going to print out? Well, I start my lap at 1, lap 1. Then I go on to lap 2, lap 3, lap 4, until I've run all 10 of my laps here. Right? And that's how this loop behaves. Again, the initialization condition is here. The continuation condition is right next to it. And then the increment, or working towards that termination condition, is right next to that. Oh, that's too big. There we go. That's a little bit better. So let's take this over to our environment and start talking about the actual syntax here. So for loops. Oops. Let me go ahead and put that into code mode there. There we go. All right. So for loops have the three main parts. The initialization, the continuation, and the increment on the same line, right? Followed by a loop body. The loop body follows the for line with an opening and closing curly brackets. Right? Anything inside that loop body will execute once for every iteration. Right? Okay. So let's do keep it down a little bit. All right. So we've got our laps here, 1 through 10. What I want to do, I actually want to show another tool here. You might find this useful. If you just go to pythontutor.com, this is not a Python course, but it's got a C mode here. What you can do is you can cut and paste code here and then visualize its execution. And I'm going to visualize this execution for how it's actually working. And then we'll go back and we'll understand each one of those nuances. So I'm going to step through this line by line. Right? So I'm coming to the for loop here. I, what value does it have? It has a question mark value here because it has not been initialized. So when I go into this for loop, it gets initialized to 1. Right? That's this int I is equal to 1. Then it goes into the loop. And why did it go in the loop? It checks, is I less than or equal to 10? Well, is 1 less than or equal to 10? True. So we execute this loop once. Right? We print out lap number 1. Then we come back up to the top of the loop, having incremented I by 1. Watch as it goes from 1 to 2 here. Right? That's what this plus plus does. It simply adds 1 to the variable. Okay? Then we go into the loop again. Why? Because 2 is less than or equal to 10. So execute this print statement. And fast forwarding here, right? It's going to print out each one. Each time it goes to the top of the loop, it checks, should I continue? Should I keep running these laps, right? Every time it gets to the bottom of the loop, it's run 1 lap. So it executes this plus plus here and adds 1 to I, right? Next, next, next. Now at the end, what happens? I is 10. Is 10 less than or equal to 10? Yes. So we execute 1 more time for the 10th lap. At the end of that loop, what value does I have now? 11. I don't know if it's going to show it or not. Yeah, it's not going to show it here. It goes up to 11. says, is 11 less than or equal to 10? No. And it breaks out of the loop and continues with the rest of the code. To show you that it continues with the rest of the code, I'm simply going to have a printf done command here, right? Recompile this and show you that indeed the program does continue after that loop is done. So some observations here. Observations. There we go. All right. The continuation condition. Actually, let's start with the initialization condition. The initialization statement is only ever executed once before the first iteration of the loop. Right? We initialized I to 1, our first lap. The continuation condition is checked at the beginning of the loop. Right? If it is true, it executes one more time. Right? If false, it breaks, here I'll put that in quotes here, breaks out of the loop. Right? And normal sequential control flow resumes. Right? It just goes with the rest of the code. If you've got statement A, B, C after that, it goes and executes statement A, B, C. Right? The increment statement is executed at the end of each loop. Right? Remember that we went from lap 1 to 2 to 3 to 4. We did that at the end of the for loop. Okay? Of course, it uses the keyword for, etc. Right? Another observation here is, what is the scope of the iterator variable I? There's a question there. Right? So remember what scoping is? When you declare a variable, where is that variable good for? Right? Where can you see that variable? That's literally what scope means. What pieces of code can see that variable? Let me go ahead and go down here and try to print out the variable I after I'm done with it. Right? I now has a value of %d end the line. Right? Well, what value would it have had to break out of that loop? What was it again? 11. I've already run my 10 laps. All right. Now I'm going to go. Now it's 11, so I broke out of that loop. But am I going to be able to print it? Nope. Why? It says, what is I? Right? If I tried to print out x, right, would you have expected that I can print out x? Do you see a variable x anywhere here? No. No such variable was declared. But variable I was declared. But it was declared where? Right here. Right? In the loop. And only for the loop. It only exists inside the loop. It doesn't exist before the loop. It doesn't exist after the loop. It is only scoped to the loop. Very, very nice thing to have. In general, you want to make sure that your scope of your variables is as small as possible. Right? The worst possible thing that you could do is have a global variable. Right? Number of students, right, equals 158, I think we're at. Right? Do not do this. This is a global variable. Why don't you want to do this? Well, first of all, globals, there's a saying, globals are evil. Right? They're evil because if you have a global variable, any piece of the code can see that variable. Any piece of the code can change that variable. And therefore, you have to test for the eventuality that any piece of code will change that variable. Right? Chaos. There's no way that you can manage that chaos at all. Do not do that. Globals are evil. Now, something that is global but is not a variable is, say, mpi. Right? Nobody can change that because it's a preprocessor directive. That's perfectly fine. Right? No, every piece of the code can see it, but none of the code can change it. So that's okay. Right? That's not a global. Right? It's a global constant, which is perfectly fine. Global variables are not. So you want to make sure that you're scoped down as little as possible. An alternative, in fact, old school C, 30 years ago, this is what you had to do. Create the variable outside the loop, initialize it in the loop, and now it does exist after the loop. Why? Because I declared it before the loop even existed. Right? Let me go ahead and show you that this actually works, and that it will retain its value of 11 at the end. I now has a value of 11. Don't do that. Write modern, nice, locally scoped loops. Right? There. Again, in old school C, you couldn't even do this. Like pre-1989, you couldn't do this. Right? But we are no longer living 30 years in the past, so do it correctly. Right? So what is the scope of the iterator variable I? It only exists for the loop, or inside the loop, right? It is updated in the loop. It changes in the loop, but it does not exist after the loop. It does not exist after the loop, right? In general, scope your variables to as small of a scope as possible, right? And going just the opposite, globals are evil. Globals, in fact, I'm just going to put that in the note so you remember that. Globals are evil. And I'm going to make sure that it's all capitals on the first letter of each one of those. Yeah? Yes, well, you could do if you did something like this. So the question was, can you change? Can you set I to whatever? And yeah, you could say x is equal to 1. Oops. And then you could say I is equal to x. That's kind of pointless though, and it does not marry those variables, right? X does not change. I will change. It's just initialized to that one variable at that point. And that's only the initialization condition is only ever executed once before the loop starts. Right? Undo, undo, undo. There we go. All right. Note the syntax. Syntax notes. All right. What kind of syntax do we have here? We've got the initialization condition. What terminates that initialization condition? A semicolon. We've got the continuation condition. What terminates that? Semicolon. We've got the increment here. What terminates that? Nothing. Don't ask me why. I do agree that it's not consistent, right? That the first one is an executable statement. It deserves a semicolon. The last one is an executable statement. It deserves a semicolon. The third one is not an executable statement. It's a condition. It should not have a semicolon. I didn't write the thing, right? Don't ask me. It is bad syntax, right? It is, at least it's not bad syntax. It's just inconsistent syntax, right? Semicolons, colons, and the initialization and continuation condition, but not the increment statement. Again, don't ask me. I didn't write the thing. Right? I would have written it differently. Right? The loop body has opening, closing, curly brackets. And of course the style, right? The opening bracket on the same line as the for statement, for keyword. Right? And the closing is on the same indentation level as the F in the for. All right? And the loop body is indented. Right? Get into those habits of writing code like that. Some people like to put more horizontal space here. I don't think it's necessary. If you're going to do that, that's inconsistent because I did it on the first one, but not over here, right? That's consistent at least. Whatever you want to do, fine, but be consistent about it. Right? Okay? Questions on that so far? All right. That's how the loop bodies work. Now let's introduce that new syntax. Right? I++ is shorthand for add 1 to the variable I. There we go. So all it does is it takes whatever's stored in I, say 5, adds 1 to it, and stores it back into that variable, right? Likewise, you can do the other way, right? I minus minus, right, is shorthand for subtract 1 from I. Right? Both can be rewritten as, how would you do this if you didn't have that syntax? I is equal to I plus 1, or I is equal to I minus 1. Right? So why would you prefer the plus plus and the minus minus instead of writing it out longhand there? Right? Well, it's shorter. Shorter to write, yeah, but you're only saving like 2 or 3 characters. Who cares, right? But it is also shorter to read. And when you get into the habit, when you get used to something like that syntax, then you get to be able to read it a lot faster, right? And that's actually where the vast majority of your time will be, reading code, understanding code, not writing code, right? If you wanted to write out how much time you spend coding, then reading is probably, say, 20%. And I'm just pulling these numbers out of the air. Understanding is probably another 70%. And then the remaining 10%, that's when you're actually writing code, right? The vast majority of your time will be spent reading and understanding other people's code so that you don't have to start from scratch, right? And if you can get by with faster reading and using shorthand stuff like this, then you do it because it's easy. You can read stuff faster and understand it faster. It also goes into what's called syntactic sugar. This is syntactic sugar. Right? So I always use the example of, say, oatmeal. Oatmeal is not very appetizing. So what do you do to oatmeal to make it taste better? You put sugar in it, right? Now it tastes sweet. Language is the same way. Why do we have 50 different, or dozens and dozens and dozens of different adjectives for the same thing? Good, super, awesome, cool, right? Things that mean the same thing. Why do we have so many words to describe that thing? Because language, we like our language to be rich, right? We like connotation. We like nuance. We like flexibility. Same thing with code. We like our language to be a little bit flexible. You can do one thing multiple different ways depending on the context. That makes the language a little bit richer. Right? Not all languages support these two things. If you're coming from a Python background, can you do this in Python? The answer is no, right? You can do it. You could do it in Swift at one point, and then they took it away. Don't ask me why not. But the vast majority of programming languages do allow you to do something like this. Something that is supported in Python and C and Java and most other programming languages are also, you can also use compound assignment operators. So here you can do things other than one. Plus plus, minus minus only ever works by one. You can write I is equal to I plus 10, right? Can be shorthanded as I plus equals 10. Is that me? I don't know. All right, there we go. So that's a shorter way of writing it. Now, did you actually get away with saving any characters? Not really, just the I, right? And maybe some horizontal white space there. But that's a way that you can improve, you can write it quicker, you can write it shorter. It also works with all of the other operators. I is equal to I minus 5 can be shorthanded as I minus equals 10, or sorry, not 10, 5, right? Vertical. It also works with multiplication and division. I is equal to 2 times I. Something, I don't know if that's me or not. Sorry if it's somebody else. It sounds like the ITS thing here, but anyway. Can be shorthanded as I times equals 2, right? There we go. What am I doing there? I'm multiplying it by 2. I'm doubling it. It also works with division. I is equal to 2, or I divided by 2 can be shorthanded as I divide equal to, right? Now you do have to be careful there. That's an integer, isn't it? So 10 divided by 2, what is that? 5, we all know that. But what about 11? 11 divided by 2, what is that? Also 5. Why? Because of integer truncation. 5.5, but it's an integer, so what happens? 5. Right? The fractional part gets chopped off and thrown away. Right? So careful integer division. Right? Okay. All right. So that's a for loop. There's also a while loop. Right? Spoiler here, why do we call it a while loop? While loops use the keyword, what do you think? While instead of for, right? So I'm going to come over here to my code, and I'm going to rewrite this for loop as a while loop instead. Right? Now, the main differences are that the initialization happens before the loop even begins. Then we've got our while loop and our continuation condition. While I is less than or equal to 10, we will continue to print it out. Right? I'm also going to put in I++ at the end here of the loop. This loop will perform exactly the same way. Oops, sorry. What did I do? I forgot my opening bracket. There we go. This loop will perform exactly the same as our original for loop, running lap 1, lap 2, lap 3, all the way up to lap 10, and then you're done. Right? All I did was take those 3 elements and separate them onto different lines. I took the initialization and put it before the while loop here. The continuation was tied to the while loop with the same opening and closing curly brackets, same style as before. It's all indented. I put the I++ at the end of the loop in order to get the same behavior as a for loop. That suggests that I can have some flexibility here. What if I did it at the beginning of the loop? Let's walk through it. I is 1. Is I less than or equal to 10? Yes. So go into the loop. I++. What did that do again? Adds 1 to I. What's the first thing that gets printed? 2. What's the last thing that gets printed? 11? Let's find out. And let me clear out the terminal there. There we go. Indeed, we start at lap 2 and go all the way to lap 11. Right? Because I changed where the increment was. With a for loop, you have no choice. It always happens at the end of a for loop. With a while loop, you can put it at the top at the beginning. You can put it at the end. You can put it somewhere in between. Right? Another consequence of this. Tell me about that I. Printf. I is now ... now %d end the line. I. Am I going to be able to print out I now? Yeah, why? It's initialized and declared before the loop. Its scope now is in the entire function in main. I is now 11, right? Remember that I moved the I++ down at the bottom. We broke out of that because I was 11. It's no longer less than or equal to 10. Okay? So let me go ahead and put this into our notes, and let's note those differences. Okay? Of course, the difference is while instead of for, right? Both spelling and pronunciation. But the initialization statement is before the loop. Right? The continuation is the same. It's tied to the while keyword. Right? And the body is the same. Right? Opening, closing, curly brackets, indentation, etc. Right? But the continuation condition. Oh, the continuation condition is checked at the start of the loop. That's also the same, right? But the increment statement can be located anywhere you want. The start, end, or middle of the loop. Right? And the other major difference here is that you cannot scope an iterator variable, iterator variable to the loop itself. Right? You are forced to deal with that variable now that it exists after the while loop is done. Okay. Let's focus a little bit more on that. What I just said there, that you can locate it anywhere you want. You can locate it at the top, at the end, or in the middle, or maybe forget it entirely. Uh-oh. I'm no longer making progress towards my termination condition. This is the coach not counting my laps. Keep going, keep going, keep going. What is this going to print? Well, first of all, does it compile? Yeah. Right. You can do this. What's it going to print? Lap 1. All right, that's less than or equal to 10, so print lap 1. Do I change it? Nope. Go back to the top. Is 1 still less than or equal to 10? Yep. So print 1, or lap 1, right? I'm always and forever running that lap 1 over and over and over again. This is an infinite loop. As long as the computer is on, and as long as we've got a network connection here, it will continue to execute. Right? First law of thermodynamics. An object in motion will tend to stay in motion unless acted upon by an external force. This is going to go on and on forever unless I act on it as the external force. and kill it. What did I do there? That caret is control, and C was C. Right? Control C kills whatever the current working program is. Right? And that will mean that you can, if you ever get stuck in an infinite loop, fine, just kill it with control C. Be careful. Right? Infinite loops aren't that big of a deal. It's just that it's just going on forever. Okay? All right. So you can't, note, if you get into an infinite loop, you can kill the program with control C. And by the way, that works for Windows and Mac. It's the same on both platforms. Right? Okay. Let's see. What if I did something like this? Predict. What is this going to print? I start I at 100. I'm on my 100th lap right now without even trying. Right? Is I less than or equal to 10? Nope. So this will not be true even before the first iteration. And it will jump down immediately to line 14. Did it print anything? Nope. Done. I is now value. Did we change it? Nope. 100. So, oops, I need to recompile it, sorry. There we go. Done. I is now 100. You can have loops that don't execute ever, right? You can. That's certainly possible, right? And you can always do the poor man's debugging of printf. This is loop number blah blah. Variable values are blah blah, etc., and you'll get into the habit of this until we break you of that habit when we introduce you to a proper debugger, GDB in week 8 or something. But until then, yeah, okay, go ahead and do that. But know that you don't want to get into that habit long term. All right? Okay. With the remainder of our time, that begs the question, right? Which one is better? So, which one is better? For loop or while loop? I don't know. Which one do you like better? This morning I said if you have an irrational fear of W's, then maybe you just want to go with for loops all the time. If you have a fear of F's or something, maybe you want to go with a while loop all the time, right? Just joking, right? Okay. Any loop, any for loop, can be rewritten as a while loop and vice versa. So why do we need 2? Right? In fact, we have 3. C also supports what's called a do-while loop. I'm not going to even cover it because it's brittle. It has a completely different behavior where the continuation condition is checked at the end of the loop. You can always rewrite that as a regular old while loop. If you're interested, go ahead and read more about it in Zybooks or in the other textbook. Right? So why do we need 2? Well, again, it goes back to that expressiveness. Sometimes you want your languages to be flexible. Sometimes it makes sense to use one loop, conceptually use one loop, and sometimes it makes sense to use another loop. When? In general, if you know how many iterations up front you are going to execute the loop, then you use a for loop. Right? If you don't know how many iterations up front, then use a while loop. Right? The difference is not that big of a deal. It's natural. All right? And I'm putting that in the quotes there because you'll get the feel for it. Right? I don't know I can't give you a hard and fast rule on when to use one over the other. It'll just feel right. For example, come over here and let's rewrite this as just a regular old for loop. In fact, I'm just going to cut and paste what we were doing before. Right. So why did I start out with a for loop knowing that I was only going to run 10 laps? Because I knew up front that I was only going to run 10 laps. Right? You can put those into variables like you observed before. Int n is equal to 10. Right? And then I can go ahead and put that in as a variable instead. I still know up front how many laps I'm going to run, 10. Or suppose that I read this in as a command line argument, a to I of argv sub 1. Right? Now I don't know how many. I don't know that it's going to be 10. I don't know that it's going to be 20, but I do know that it's going to be n, right? We are only going to run laps 1, 2, 3, 4, 5, all the way up to n. Even if it's a variable, I still know how many laps I'm going to run. Right? Here's another example where we do not know how many laps we're going to run. Right? So, given a number, x, compute how many digits are in it. For example, if I have 1, 2, 3, 4, that has 4 digits. Right? Another example, 1, 2, 3, 4, 5, 6, 7, 8 has 8 digits. Right? How many digits does 0 have? 1 digit. Right? So I want to write a program for the remainder of our time here that does that. Okay? Ideas. How could we go about doing that? We could use some math tricks. We could use some advanced string tricks that we haven't gotten to yet. I don't want to do that. I want to use code. I just want to purely code this. Right? The math trick is using log base 10. That tells you, and then stealing it. That tells you how many digits are in it. Right? That's what logarithms are. Right? So ideas? Let's start out with that. Let's whiteboard it. And I don't have a whiteboard here. In fact, we're down one screen. Sorry again. I will try to rag them out again on that. But 1, 2, 3, 4. Right? How many digits does it have? 4. Here's a hint. What if I were to divide it by 10? That would result in 123.4. But if I did integer division, what would happen to that 0.4? Truncation, gone. What if I were to divide it by 10 again? What does that give me? 12.3, but because of integer truncation, gone. What if I were to continue to do that until when? ... We've got down to 1 divided by 10 is equal to 0.1, but integer truncation makes it 0. Right? So that's called whiteboarding. Even though I didn't have a whiteboard, right? I worked out one example on a visual medium here so that people that I was working with, you folks, right, could see it and you could add your own input to it. When you're doing your hacks, when you're doing your labs, whiteboard stuff, communication, right? Draw stuff out. Yeah.
So what you're saying is you could abuse the rule of integers to go 4 while x doesn't equal 0, repeat the divisor and add 1 to a variable.
Right. You just divide by 10 until ... It is what? When did we stop? 0, right? Keep a count of how many times you divide, and that's the answer. Seems simple. Let's try it. But before we try that, what kind of a loop do we want to do that here? Because it says do this until, right? A while loop. Why? Do I know how many iterations I'm going to go up front? Do I know that I'm going to go 4 iterations or 8 iterations? No. If I knew that I was going to go 8 iterations, I'm done. Right? Why am I even doing anything if I know that there are 8 digits in that number? Right? So let's use a while loop instead. While something, I will continue to divide by 10. So now I need a number here. Int x is equal to, we'll go ahead and try it with 1, 2, 3, 4 initially. X is equal to x divided by 10. Right? And I want a counter. Int num digits. What do I start that out as? I don't know. We'll come back to it here in a second. Right? Num digits is equal to num digits plus 1. Why? When you divide by 10, okay, that's 1. One time I did that. Right? Now I'm at 123. Right? 3 digits left. Divide by 1. Right? Now I'm at 12. Now I'm at 1. Now I'm at 0. Right? And there's my counter. Right? And then at the end, let's print it out. Printf. Number of digits, %d and line, num digits. There we go. Now we have to go in and fill in the blanks. While what condition again?
X not equal to 0.
Okay, x is not equal to 0. Right? Or it's, I'm going to change that because you went immediately to the better answer. I'm going to go ahead and go with x is greater than 0. Right? We'll find out why here in a moment. Right? Where do I start it out? 0? Okay. Why? Well, because, 1, 2, 3, 4, I will end up doing this 1, 2, 3, 4 times. right? If I started at 1, then what do I get? 5 digits? That doesn't make any sense. Right? So let's go ahead and test this. Right? Now I'm going to be doing ad hoc testing here. Right? I'm going to be just doing compile, test, compile, test, compile, test. We were demonstrated to you in your lab yesterday of an alternative, writing more formal, informal unit testing for your leap year function, right? Where instead of having to compile, redo it, compile, redo it, compile, redo it, you coded up your actual tests so that you didn't have to redo that every single time. If you change your code, you fix one bug, you go ahead and rerun the entire thing and automate that process, right? Number of digits is 4. Works. Change. Recompile. Test. Works. Done. 2 test cases. We gave you 3 test cases yesterday and told you to do 3 more. Why? For code coverage, right? Yeah, go ahead. Question?
Let's try x equals
7?
7.
Okay. That's 1 digit. Yeah, that works. Right. What doesn't work?
0.
0. 0 has 0 digits? Nope. Sometimes you have corner cases, edge cases that have to be taken care of differently. I hate it, but not everybody is in calc maybe. But what happens with 1 over x, the function 1 over x? Is it different? What does it look like? It grows until what happens at 0? Can you divide by 0? Nope, it blows up. But you can still differentiate that function. You can still integrate that function as long as you stay away from 0, because that 0 is the edge case. Here, 0 is our edge case as well. So if x is 0, then treat it differently, right? Printf, and in fact, I'm just going to steal this here. Number of digits is 0. There we go. And then, of course, exit the program, exit, because we're done. Right? Otherwise, put everything else into an else statement or something. Oh, you're right. Thank you. There we go. There. Number of digits is equal to 1. But I changed my code. What I have to do now is go back and do regression testing. Did I break any of that stuff that worked before? Which means I'm going to have to go back and try 1, 2, 3, 4 again. I'm going to have to go back and try 1, 2, 3, 4, 5, 6, 7, 8. I'm going to have to go back and try 7. I will assure you that they all work, but that's because this is a simple example. What if I had coded all that up as an informal test suite, right, like you did in your lab yesterday? Then I wouldn't have to redo all that garbage. Right? I would just have to recompile, run it again. All the test cases pass now still. Right? I don't have to redo all that work. I heard another suggestion. Negative? Yeah. -7. How many digits are in there?
1.
0. Why?
Because x is greater than 0.
Yep, immediately. -7 is not greater than 0, so we never end up dividing anything, right? -777. That won't work either. Okay. Suggestions on how to fix that. One of them would be to, like you suggested, not equal to 0. What's another one?
If you added the math library.
Okay. We've already got the math library, so how can we bring that to bear here? Take the absolute value of x. Is that correct? No, that's math, right? This ain't math. This is code. It's abs. And it's abs because it's an integer. If this were a double, what would I use? Fabs, right? Just fabs, yeah. There is no dabs. There is labs and labs, and we'll talk about those later, right? But here we use abs, okay? Now do those work? I've got -777. It should be 3. Excellent, right? Now, if I were doing this in a real context, in real code, I would have written these test cases maybe even first. A test case is an input and an output pair that you know to be correct because you looked at it and you did it on a calculator or something like that. 777, there are 3 digits there, right? 1, 2, 3, 4, there are 4 digits there, right? Those are my test cases, and I would codify that by writing them out as proper test cases. informally, or later on, we're going to use a more formal test case, unit testing framework called CMACA. Right? Questions on that? Otherwise, I believe it works all over, right? And I will go ahead and put this into the notes so that you have it. But now do you understand when to use, when it's natural, I should say, to use one versus the other? You use a for loop if you know I'm only gonna run 10 laps, right? Oh, by the way, speaking of which, remember that we do have a run with faculty, a monthly event. The next one is Monday. If you want to show up outside of this coming Monday, I think. If you want to show up outside of Shore at 9 a.m. to do a 5K, I have to do it virtually because I've got classes all day, and I'll be doing probably 15K instead. So if you want to come and do a 5K, if you want to do it virtually, right, then do like 1K, 5K. We can walk it if you want to. Just post a picture or post it to your social media, to the department, and join with running with School of Faculty, right? The School of Computing Faculty, excuse me.
If you're not going to be there in person, are you just going to be on like a screen with wheels on it?
Oh no, I'll do my running at 5 a.m. when it's cool, nice and cool, not hot.
Would it be funny if I programmed a robot to do my running for me?
Sure, go ahead.
Mile distance does not equal 5K. 1 kilometer.
You can.
Kilometer count.
Bonita is a roboticist, so you suggest that to her too. All right, we'll see you on Friday.